So here we go, continual learning for the open world. But really, this talk is about continual learning and how we talked a lot about how important it was and about how it played this critical role towards AGI and how we kind of missed the mark. Um, yeah, so let me get started here. So I was interested in continual learning because I thought it was essential for artificial general intelligence, whatever that means. So, and it's kind of obvious, right? I mean, whenever I talk to the media about what I do, they're very confused because they think our AI systems learn kind of like we do. And the idea of a train and test split is kind of a foreign idea, right? That's very abnormal compared to conventional thinking. Humans and animals, we don't have fixed train sets and then test sets. We learn continually, right? So this is what got me interested in the problem when I was a graduate student, like, I don't know, um, um, maybe I first learned about the issue in around maybe almost 20 years ago, these old papers. Um, Anyways, a human like AGI, we need to learn more like us, continually and efficiently, right? So that was what I was thinking. And then I've been working a lot in this field for, about a decade now. Um, and I wasn't alone in my thoughts about that. So here's a classic paper in continual learning, overcoming. This is the EWC paper, and I've highlighted the words AGI and the first, I guess, four words of the paper. Right? I wasn't alone. So, did the pursuit of AGI inspire anybody to work on continual learning here? Uh, but did we even need it? I mean, everybody's already saying maybe we already have AGI of some sort at least. Can you feel the AGI right now? Is it coming soon? There's a lot of money being thrown around on it. Yeah, can you feel the AGI? And so why do we even think that? Well, what does AGI mean? The G is general, right? And at least since GPT-4, we had human-like performance on professional benchmarks. I use these things all the time, and they can do things that would be very challenging for me. At least they would take me a lot of time to do, versus, it can do it almost instantaneously. And GPT-4 is old, right? These things are doubling in capability every 7 months, the frontier models. So extrapolating in 5 years, they'll be able to autonomously complete work that requires 1 month of human labor. That sounds pretty general. Here's just some more benchmarks, right? It's looking great. Like it's working, it's really crushing it compared to humans. Maybe it's already here, right? Here's a bunch of predictions, right? Sam Altman 2025, Elon Musk 2026, all these different people at different dates that they change over time. And not only that, people talk about the Turing test as being something, well, they've long passed the Turing test, and now people are falling in love with these systems. He used Grok's sexy AI bot for dirty smut, then he fell in love. All right, this is, I haven't tried out that version of Grok. So aren't these AGIs? They pass the Turing test. They don't have continual learning of the kind that I envisioned, which was changing your weights over time. But they are generalists. They can do many tasks. In many ways, they're superhumans, not just AGI, ASI. They know far, far more than you or me. Like their breadth and depth is far deeper. People fall in love with them. That makes me deeply concerned, actually. A lot of people don't understand how they work, and so they have way they anthropomorphize them too much. Um, they continue to learn, sort of, right? I mean, they got RAG, right? I mean, is injecting a text into your context window is that continual learning? You can just keep growing your vector store. I don't know. Um, well, right now, so in the my introduction, it was stated that I work on towards AGI, and that's true, and that's what I want to say. But recently, I've been thinking we gotta. I don't like the term anymore. Like the term has become very overloaded and confusing. Um, so pre-2020 definition of AGI would be something like this: a machine intelligence with human-like generality, able to continually learn new tasks, transfer knowledge across domains, reason flexibly, and adapt to novel situations at a level comparable to or beyond human cognition. This is what I wanted to work on. What do we have now? Well, the definition got tweaked. Uh, Post 20, this is the definition used by these companies, highly capable autonomous AI systems that can perform most or all economically valuable tasks at or above human level across a wide range of domains. Goal, measure impact by what systems can do in labor and productivity terms. Not about human-like, right? And do they even need a continual learn? Do most people for their jobs need a lot of continual learning? I don't know. Um, um, so I wrote this essay, which at least got some attention, saying I think we need to retire this term. I need to figure out what to call what I do. Right now, it's like I've I started to say I work on synthetic minds, but I'm not sure if that'll catch on or not. Um, um, but anyway, so now, given that, we can think about continual learning as maybe having two different optimization targets, right, for these two different forms of AGI. We can have the foundation model destination, that's this economic AGI, efficient learning and generalization for large pre-trained foundation models where we aim to preserve base breadth while keeping the model up to date. That would be nice. This still not maybe not human-like, just keep it up to date, right? Instead of having a cutoff date. I think of that like, I don't know if anybody watches Star Trek or used to watch Star Trek, right? But it's like the ship's computer. So the ship's computer is really like an AGI, and it's almost like how I use LLMs right now. I'm like, hey, can you find this? What about that? Is that true? Is this true? Can you find some flaw in my logic here? Right? And they're very good at that. Now, are they good at true creativity, true knowledge discovery that's not mixing and matching? I'd argue definitely not. But in terms of like having all of our knowledge, current knowledge, right? They're good at that. Um, the kind I was interested in working on, and maybe this is still just because of my Star Trek liking, is more like this guy, Data, right? So human-like synthetic minds, lifelong learning and self-improvement, where the AI continually learns new skills, retains knowledge, and self-improves over time without human intervention, capable of metacognition, social awareness, and potentially self-awareness. Here, maybe even being, got self-aware, maybe it does make sense for you to fall in love. I don't know, but you fall in love with a ship's computer. It kind of doesn't make a lot of sense to me. On the other hand, I think this one's important because for all these people worried about a AI doomer, and people saying you shouldn't even have kids are going to kill us all. They're worried about Terminator here. I don't think this can get there, right? I don't think this current path, this current trajectory can get us to that. You're not going to be self-aware. They're not going to have motivations. It just, could somebody use them for bad things? Sure, but that's the human doing them. They're not autonomously doing it on their own. On the other hand, if you're self-aware, I still think this is very improbable for a variety of reasons. If you're interested, you can find my blog and why I think it'd be irrational for them to do this under most criteria. But regardless, I think it'd be worthwhile to study this. Anyways, so that's just the start of my talk in terms of like setting up the tone. So first, I'm going to talk about continual learning, optimize the wrong objective. Second, continual learning for foundation models, and then I'm going to talk about and towards efficient continual learning of foundation models and forward transfer and out of distribution detection. Very relevant, I think, for this workshop. So first, a little bit. So for context, this is a version of a talk I gave to a bunch of the continual learning leaders in terms of like a thought meeting about, what's the future of the field. So I'm kind of giving you guys a version of that. So I would argue we optimized the wrong objective as a continual learning community. And where the wrong objective was this is made by an AI, didn't do a great job, was lowest forgetting was the target versus retention and transfer per update. That I think was the right objective. So here's about the time when I first came out with my first papers on this topic. I was with my student Ron here. He graduated a long time ago. And since then, the number of papers, this is class incremental learning, this is continual learning, right? It's increasing, maybe exponentially per year, right? So you think we've made a lot of progress towards the AGI for continual learning part, but if anything, we really screwed up, somehow missed the mark. So status quo for continual deep learning, and in part, I kind of blame myself for this. I put out some pioneering papers, I guess, which then people kind of, I think, got too stuck on, right? You're trying to make the first steps in this field versus saying this is how it should always be done, So status quo and continual deep learning. Definition: learn from non-stationary streams while retaining prior competence and avoiding catastrophic forgetting under limited memory and no access to past data. Well, you have access to past data limited to that memory. Core focus and practice retention metrics on disjoint tasks doesn't match human experience at all, right? Our tasks, we don't do class incremental learning. That's like a very adversarial scenario. It's interesting, it's a test, but why do we have all these papers written about it? It's useless in the real world, right? It's like an interesting adversarial test. And now people design algorithms around it. Replay minimized. Why? It works. Well, because we don't like it. Bounded, bounded memory. Their implicit assumption is models start near blank slate and should still remember everything. Does that make much sense for forgetting? Um, I mean, children, can you remember what your life was like at age 1? How about 6 months? How about 2, 3, 4? Do you think your objective was was not forgetting at that stage? No, you literally forget everything. It's called infantile amnesia. You can't remember. Your brain is not trying to optimize for that. I would argue it's trying to optimize for your ability to learn future stuff more efficiently. So here's my paper that won awards for best paper of 2019 and in the for based on its impact over the next 2 years in the journal Neural Networks. And here's this other one, measuring catastrophic forgetting in neural networks. I was very focused on forgetting. Why? Was I and why were others? Well, I had to start somewhere, right? And that's what the old papers told me, and there was nothing out there at the time. So since McCloskey and Cohen, it's classic work. Catastrophic forgetting was the striking failure mode, right? Easy to reproduce, easy to quantify, devastating in magnitude. So that's what we did. We defined it in opposition to forgetting, and then we had these very simple benchmarks we constructed that were really, really toy. I started arguing against that very early on. They were designed to exaggerate forgetting. And we created special algorithms for these scenarios rather than treating it as distributions as tests, right? People started having a special algorithm for a distribution rather than saying these distributions should be tests. We had very convenient metrics for retention curves, for getting scores, and then it kind of resonates, right? Catastrophic forgetting sounds great. It's catchy. One thing that I think this field has also done is because we keep using the word catastrophic forgetting, everybody thinks we've made zero progress. I was at this big meeting that the US government put together on the future areas to invest in AI, and a bunch of the groups said, well, one of the most important things we've got to address is continual learning thing, nobody, because of the catastrophic forgetting, and said nobody's made the progress. I'm like, well, that's because we still call it catastrophic. So it sounds bad, right? If you're just looking at anyways. So this is what a lot of people do, and it's absurd. Yeah, so this is what we did. Gosh, I'm getting phone calls. This is what we did. The expectation is learn the correct label and don't forget. This is a lot. So here's day 1, learn cats. Day 2 of a kid's life, learn buses. Day 3, learn airplanes. Day 4, learn elephants. And they can barely see anything. This is what the analogy is, right? This is what people try to do. Like, this is class incremental learning. If you start from scratch. In terms of like babies, concepts are decodable from infant fMRI recordings after about 6 months. So not day 1. They don't even have the necessary kind of internal representations to really learn these things. They're set up. What they're doing is learning representations, not trying to remember what a cat is. So primates invest early to build reusable features, enabling learning faster, better. We train foundation models to learn representations prior to fine-tuning. Learning efficiently seems much more important from an evolutionary standpoint and from a compute perspective than worrying about storage. Like, everybody started worrying about storage for no reason besides replay worked too well. So moral, representation building precedes and enables stable retention and forward transfer. So it would be like a more baby-aligned version of this. So continual deep learning is about building and reusing general purpose representations over time, not forgetting, right? The network starts with some representation base, pre-trained maybe, self-supervised, random, different constraints, right? The baby be somewhere between random and, they have some inductive biases and things. Anyways, then learns from evolving streams while preserving prior competence and leveraging accumulated structure so that so that each new capability they learn is cheaper to acquire, right? Getting better sample complexity over time, better representations afford that. Forgetting is more like a failure mode, right? It's a failure mode, especially once you actually need to remember stuff in order to kind of survive. But representation growth and forward transfer should be the objectives. People barely ever even measure these things, usually because it's like negative. So, it doesn't look good, so abandon it. Rather, well, hey, this is alarming. Why don't we try to deal with this? So why did we constrain storage? Another thing that I think really screwed us up. Just we sabotaged ourselves. Rationale was maybe partly cognitive, but then we really screwed that up too. So we have a brain region called the hippocampus. It's like this little kind of buffer. If you destroy your hippocampus, you basically can't learn new things. It kind of, I mean, to put it into LLM terms, it's kind of like your vector store. But it selectively stores things in compressed episodes. So you experience life in a temporally ordered fashion, right? It kind of temporally compresses it. And during a certain phase of sleep, it kind of is distilled into your long-term representations. There's a phase called NREM. So it's kind of like distilled for long-term storage. So that's a little different than our RAG models, right? So you think of it as like a buffer that gets distilled. When you're stored in like a latent space, not raw text or pixels. Another reason why constraining storage, edge devices may not have it, but this actual replay is actually done in our brains. We know that happens during non-REM sleep. So during non-REM sleep, these latent experiences are reactivated for this distillation process. Again, I'm using machine learning terms. Neuroscientists probably be very annoyed with me. I'm just trying to map it on. And we showed in some early work, back in 2019, that if you just did this with an unlimited buffer, it wasn't computationally efficient, but it worked. Basically, you solved this problem. So we already solved it, kind of. Maybe then the next question should have been, how do we make this efficient versus we should abandon it? Just in terms of just pure economics and what companies are interested, they could care less about the storage question, right? Unless you're learning on an embedded device. Storage is cheap. Compute isn't. Foundation model training keeps everything. The bottleneck is GPU time, not bytes. So we need continual learning to be efficient, right? And I would like to argue continual learning should become ultimately the default mode of learning for these things. Yeah, this is just saying more of our things that we did what were wrong. I'm just going to move on from that. So just a couple other thoughts about why continual learning is relevant in today's kind of foundation model era. So if you kind of look at ML engineering books, right? So these are people just focused on deployments and stuff like that. They'll talk about continual learning, but their notion of continual learning is different. They'll talk about model drift. So model drift is you deploy a model in production. It's not randomly initialized. It's a good model, right? And then it goes down over time, right? They track some metric and it gets worse. The world changes, users change, whatever happened. It's called model drift or model decay. And so they'll say, well, we do continual learning. You keep storing new data and then you retrain the model. There's one paper from Grubhub about this. So Grubhub figured out how to use continual learning to better serve their, I guess, make predictions to improve money. And you can see why this would be useful, not just in terms of like maybe computational efficiency, right? Can be very expensive to retrain, but also if you can keep this thing, more closer to flat, right, versus going down, you make more money. Yeah, so here's an example from this course from UC Berkeley, full stack deep learning, where they're like, this is continual learning, where it's like retraining trigger. They retrain from scratch, right? You monitor when things go down, you retrain. You goes down, retrain. Retrain from scratch, right? Is that continual learning? I don't know. I think we need better methods. But so why are all the methods being ignored? Well, I put out this paper a while back where we were just looking at a bunch of methods for vision. And it turns out they not only work worse than, so this offline is just trained with all the data, retrained from scratch, right? Most models not only perform worse, they're more computationally expensive than retraining from scratch. It's like pointless, right? Just retraining from scratch is going to be so much more expensive. There's a handful of, like this was one of my old models with Tyler Hayes here, that actually still wasn't as good, but it, you know, was at least so. So on the x-axis we have number of updates. So that's the old efficiency. Um, a lot of people, myself included, put out this paper trying to argue people needed to start focusing on this issue a couple years ago. I think little has changed. Like it kind of not much has happened. You know, people I think are stuck in, you know, kind of publication bias kind of mode. Um, um, the thought about efficiency being important kind of violates reviewers' expectations. It's different. And people don't like that, I guess. But you know what I think people should do if you're interested in Q learning for foundation models or just pre-trained models, you should be starting from a strong pre-trained model that be deployed, and then you should still evaluate on those things that were deployed upon. Right. So a lot of times people will do this thing nowadays. They're like, we took a vision transformer trained on, let's say, ImageNet 21K. It's super good. We're going to throw that out. We're just going to use its embeddings. Now we're going to learn CIFAR and then MNIST. And I'm like, okay, well, wouldn't it make a lot more sense to try to learn new tasks while preserving your ImageNet performance versus throw that out, right? Because that would be much more aligned with a real world application. Yeah, so we want to evaluate based on being robust across distributions, to be computationally efficient, hopefully be increasing forward transfer as a function of learning, right? And even maybe backward transfer. See if ImageNet got better. Yeah, so that's my kind of North Star. Continual learning should be the default operating mode. So this has been the focus of at least some of my lab's work, and especially one of my students, Yusuf Haroon, over the past few years. So towards continual learning for foundation models. So we've adopted this kind of neuroscience-inspired framework where we have compute-bounded replay. So I know I've been throwing around the word replay. If you're not familiar with it, replay means you have some storage, potentially very big storage in my case, and you, as you acquire new samples, you can put them into storage. Now you may be putting embeddings into storage or raw pixels. I prefer doing this kind of in a latent space versus storing raw pixels or raw text, which feels pretty wrong to me. And again, a lot of my intuitions just come from my knowledge of neuroscience. We do not store raw activities of our photoreceptors. Our hippocampus is kind of like storing multi-modal embeddings. But anyways, and then the model alternates between wake and sleep phases. So during this wake phase, acquire and store salient samples, and then optionally do lightweight updates. In sleep phase, we update parameters using our stored samples, where we are allowed up to M updates or some other way of budgeting, you know, the amount of compute being used. All right. So we're saying we got to be efficient. And so, you know, it's kind of like, you know, our lives, right? You stay awake, you go to sleep, you consolidate, right? So that's basically what I'm arguing for, is that kind of framework. So our first paper using this is called Siesta. Reviewers hated it. It took a long time to get it published. Eventually, I just gave up and said, let's go to TMLR. They don't care about it not being aligned with past work. They're like, okay, well, this is really strong, but I don't know. They said it didn't have sufficient novelty despite being really good. Anyways, just to give you in a nutshell how the system works. During the wake phase, we store compressed experiences. So we have the first few layers of the network. So very little of the network. I think like 1 or 2% of the network is frozen. And then we basically use product quantization to store those representations in a compressed latent space. And then giving us a very strong memory efficiency and allowing us to store huge amounts of data in a very compressed manner. So this is for images, but you could do the same thing for like text or something else. And then during the sleep phase, we use this latent replay with a compute budget. So rehearsal and replay are synonyms. So we select M samples to update all these plastic layers in the network. It has some base initialization, so kind of like us as humans and that baby, right? You kind of got to learn your representations first before you can start measuring forgetting and stuff. So this is my first work on this. I'll get to the forward transfer stuff in a bit. This is a few years ago. So yeah, it basically we'd have pre-training phase on the first 100 images at ImageNet here. And then during the wake stage, it receives a sample and caches them. And then during the sleep stage, after every n samples of the wake stage, it goes to sleep. It does M updates of backprop using this buffer. It samples it takes M samples from the buffer. Here we're going to talk about better methods to do this. It sampled them uniformly per class, and we update 90% of the parameters of the network. First 2% are frozen, right? Because we're using this latent replay. And what we found when we just did this was we basically ended up with, so this is Siesta versus this star is a model just trained on all 1,000 classes, and our job is learn the remaining 900. So my student put this here, 0 forgetting, all right? And here are a bunch of other models. And then what we did is we tested it for, this is classic incremental learning. Over here, we did some hypothesis testing to basically look at the jointly trained model versus Siesta under like IID continual learning versus class incremental. You can think of IID as a very, very, again, toy situation and artificial. That's the way we normally train our machine learning models. And class incremental, I would say, is a very adversarial, weird distribution. But it's adversarial. So, and we seem like it works. Basically, my philosophy is test on the really easy and really hard. Neither of them are natural. If you can do well on both and show it's equivalent to the joint trainer, you probably are doing pretty well. And it then ended up needing 7x to 60x fewer updates than competing systems or other recent systems, 10x less memory, and had 2 to 20x fewer parameters than the current state of the art, and took only 1.9 hours to learn all of, not to learn the full ImageNet, 900 classes of ImageNet. Some of these other methods took, days, all on the same pre-trained backbone. The next question I have is, can we make it more efficient? So it uses uniform sampling. Can we identify a good policy for picking which samples should be selected, right? So we put out this paper in COLAS, the Continual Learning Conference. Whereas, to the best of my knowledge, we figured out the first practical replay policy for selectively picking things that made it make replay more efficient. Which, I mean, I chat with people at DeepMind, other companies. A lot of people tried this, but nobody figured out a policy that worked. I actually had students, try and give up, but eventually we found a way. So intelligent sampling, instead of the very, very strong baseline, is just sample uniformly from each class. Like, if you have if you're allowed M updates, if you got K classes, sample based on M divided by K, right, per class. And so this GRASP replay policy, which is very simple, is just build batches based on samples. Start with the easy ones near like a class prototype. You're sampling a certain class. Sample the ones that are closest to the class prototype, and then as learning progresses, sample further away. Right. So you want to go from easy to hard, and construct your kind of batches as a mix of easy to hard samples versus kind of like random. And what we ended up with, so this is showing versus uniform class balanced, we got the same performance as uniform class balance and 9.2 million fewer updates, but only 1.6x speed up. One thing to note is it's very important not just look at updates, but also look at flops. A couple of the models, we found a handful of methods that also purported to do this, and some of them were like, okay, they're going to pick the next sample. So they claimed, we actually didn't seem like it was that good in our own replications, but they were like, they claimed to get needed fewer updates. But when we ran their code, they were taking 30 seconds per sample to pick which sample should be replayed. kind of defeats the purpose. If I'm like, why is it so slow? If it's supposed to be faster, you can't just measure just updates. You got to measure something like flops. Okay, so the next one I want to talk about, and this work I'm pretty proud of, is improving forward transfer and sample efficiency. So how do we deal with improving forward transfer? Weirdly, it's like one of those things that should be obvious, but why is there so little work done on it? So we got this paper in NeurIPS here. What variables affect out of distribution generalization pre-trained model? What I really mean is what variables affect forward transfer. I every time I try to publish these continual learning papers, everybody says this is weird, and so I thought, okay, well, change it from forward transfer to out of distribution generalization. Great, NeurIPS. Um, um, so my work was inspired by being outraged by this paper, which came out from my friends at DeepMind here, where they argued they found this interesting effect, where they were training models, and so on the left, they're training linear probes on each layer of a pre-trained model, where they're pre-training it on a certain data set, and then this is on the in distribution performance. This is on your task one, let's say, right? And task two being the new task, right? So train the linear probes on just the task two, it kind of goes up and then down. That's concerning, right? So A, why the heck have we been using embeddings over here, right? Near the end of the network. We should all be using them in the middle. Why didn't nobody realize this? Seems like we should have realized this. Um, um, so I was like, well, this seems to go against everything. And even my siesta model I just showed you all, this violates its idea, right? It said we can keep those first couple layers frozen. You only got to train the top. Okay, well, this doesn't say that. This says almost the opposite. So they came up with this idea of the tunnel effect hypothesis. An overparameterized n-layer deep neural network forms two disjoint groups. The extractor consists of the first k layers and creates linear separable representations, and the tunnel is the rest, right? And it just hurts things. Um, um, and this is basically what they discovered independently is a phenomenon called intermediate neural collapse, where as you like neural collapse of the penultimate layer is basically inevitable if you just train long enough. But what people found is earlier layers can collapse as well into basically a fixed geometric construct, propagating from the, kind of like the output layer back a certain amount. Yeah, and then there's been a number of papers that have observed this phenomenon. In fact, some people now have proposed, great, we actually didn't even need to train those layers. We know what this ETF simplex, that's the geometric construct they collapse into, is. We can just initialize all the end of our network to that and freeze it. Just initialize it to this fixed geometric construct. Yeah. So yeah, people found this. So I was very so A, that paper kind of violated all my intuitions. B, I'm very triggered whenever anybody has big, broad generalizations and only assesses on 32 by 32 images from and C for 10. And I'm like, is this really true everywhere? So we basically did a very tightly controlled study to look at how do the properties of your data affect generalization. So we trained 64 ID backbones where we carefully manipulated and have careful paired experiments where each variable is only one variable is manipulated between each pair and everything else is held constant, where we had like image resolution. We had going from those values, right, 32 by 32 up to 24, 24, distribution class count, augmentations, yes or no. And we also had like the amount of overparameterization compared to your sample count, the depth of network, CNN versus vision transform, and a couple detailed things. And we trained 10,000 linear probes on in distribution and out distribution data sets. This is all on ImageNet. We basically created like tiny versions and created carefully constructed subsets. How does image augmentation impact this tunnel strength or forward transfer? So what we found is, this is very obvious, hopefully intuitive, it shifts the tunnel. So here, if you train with augmentation, your tunnel moves to the right, meaning your embeddings you should get move. to the right. Very reasonable seeming, right? Same thing with the vision transformer. Okay, this is hypothesis testing. Okay, what about image resolution? Here's 220/24, here's 30/32. Again, same images, just different things. That moves things enormously to the right. So if you want to really get bad forward transfer, train on C for 10 or C for 100. You get those low resolution ones, they learn very, very, very different geometries than you do on ImageNet. So they transfer in the middle. Hey, we replicated those people's study. This is exactly what they saw, right? But it didn't generalize. It generalized. It's kind of like it's local to those specific data sets. Yeah, so that had a big impact. What about data quantity versus semantic variability? Class count versus just number of things. So here we trained with 10 classes, 50 classes, or 100 classes, where each set has exactly the same number of samples, right? You could say you have, I don't remember what the exact number was, but basically these are all the same sample size, but just different amounts of semantic variability. More variability really, really, really decreases your tunnel. On the other hand, if we just train with more samples and keep our class count fixed, nothing happens. So, which kind of makes me wonder, everybody talks about, scaling laws with the amount of data. I feel like that may need some deeper thought too. Okay, what about the architecture? So impact of overparameterization. So they thought the more overparameterized, the worse your tunnel. We validated that. They were correct on that. In fact, they were correct on everything they said except that their work generalized. The depth impairs transfer. And so then we did the SHAP analysis, kind of ranked these things. So they argued that this stuff mattered the most, or that was the only thing they talked about. So, and it does. This basically, if it's negative, it impairs transfer. If it's positive, it improves transfer. So higher resolution, big impact on transfer. Augmentations, big impact on transfer. More classes, big impact on transfer. Vision transformer versus CNN, doesn't matter. If that tells you anything. Okay, so now I want to tell you quickly about this follow-up paper. I think I got to stop. But this is the most relevant, perhaps, for this workshop. So I worked on out-of-distribution detection a while back, and my PhD student, this was maybe 6 years ago, was very frustrated because I said, okay, I want to do open world learning. We got to get out-of-distribution detection to do that. Take these methods on C for 10, see if they work on ImageNet. He's like, they don't. So our paper is nothing works. Okay, where he argued it was because the features aren't right for ImageNet. Well, basically what we found is the very same kind of featural representations you learn on C for 10 are ideal for out-of-distribution detection. On the other hand, they are very bad for transfer. In contrast, the ones you learn on ImageNet are very bad for out-of-distribution detection, but great for transfer. So what we found is there's an inverse relationship between the amount of neural collapse and detection and transfer. More collapse, better detection. Less collapse, better transfer. Uh-oh. Well, then how are we going to do this? Well, fortunately, our networks have multiple layers. So can we create a network that wins everything? Like, we need a separate layer to do embeddings, a separate layer for doing out-of-distribution detection. So basically, we have our representations learned here, or here rather, and then we have a fixed projector. Hey, remember that fixed geometric construct I was telling you? Just plop it in, and it actually causes collapse. So you can just use that as your projector and then have an output head. So just to have that fixed thing, it collapses your representations. And what we found is that to decrease this collapse, we actually discovered entropy regularizers really impair the ability for your features to collapse. So using an entropy regularizer. Just to wrap up here. So this is like what these very collapsed, rather, this is what the collapsed representations look like if you do like a projection of the embeddings. And this is what like features that are good for transfer look like. But they do not look very good for doing out-of-distribution detection, as you can see. So basically, if you're interested, you can check out this ICML paper. We created a special kind of architecture with the right inductive biases as close to regularizer, which was able to achieve strong outer distribution detection. This is, our baseline outer distribution detection. Lower is better here versus our method. And then this is for forward transfer, right? So again, lower is better because we're doing air. This is our method, right? We were able to get better forward transfer as well. Okay, so the last stuff was just about how to create synthetic minds, but I think maybe I'll stop here just because in the interest of time. So, but I got to thank all my students and sponsors while I still have them. None of this work could be done without them. So anyways, I would argue Keel learning has a lot of promise. The community's kind of screwed up a lot, and I don't know. I've been complaining about it for 5 years, despite, even maybe being part of the problem by publishing some of the first papers. But it's like, you got to move on, right? I mean, I've moved on, but people kind of get stuck. We're trying to work on this efficiency thing, but more interesting to me is I'm trying to work towards both thinking about forward transfer representation geometry and how can we actually move towards this synthetic minds. Okay, thank you so much.
Thank you, Chris, for the really nice presentation. Is there any question from the audience? Yes.
Yeah. Hi, thank you so much. That was an amazing presentation, lots of very interesting content. So one question that I had was related to you talking about fine-tuning foundation models and considering scenarios where you have an initial model that is then fine-tuned for a downstream task. Do you think it's possible to then say continue training, continue improving the foundation model in an unsupervised way without having to go through the process of fine-tuning the downstream model? Or how would you deal with this? The fact that you have an initial model which you then fine-tune, and ideally you want to continue training both.
So let me understand. So you basically are thinking of this as two disjoint models. You have a foundation model, let's say, generates embeddings. You want to keep that up to date. And then you have like something that ingests those embeddings and then, for your specific task.
Exactly.
Is that right? So that paradigm is a little bit different than what I'm thinking about. I'm thinking about it as the model as a whole and that it can do things, right? So not, it's, so you could think about if you're going to include self-supervised learning, you'd think of that as like a one loss function, but you'd also have like a task-based loss function. If you were to do what you're proposing, the big challenge is going to be representation drift, right? So you'd have to combat that, which is challenging. But it's an interesting problem. I don't know of any work that's kind of defined it in that exact manner. But you can imagine if you are continuing to update your backbone, right, versus you're kind of like your top of your network, the thing using them. I guess from a practical perspective, you might ask, is this necessary? Could you retrain from scratch the other part? But that's kind of like not as scientifically interesting. But you'd have to deal with this representation mismatch. You'd have to figure out a correcting scheme to deal with that. I have a couple thoughts about how it might be done if you're interested. I don't know, are you working on this?
I am, if we have time. So I know it's a challenging problem. It's just something that the way I see it for now, whenever I have to do this, I would typically retrain the foundation model and then have to retrain this fine tuning from scratch. That was interesting. Like, yeah, what are like some general ideas that you would have for approaching this, like, from an efficiency perspective?
So if you have the two things, right? Like if you're really thinking about a separate model that ingests embeddings from the foundation model, but you want to update the foundation model, and update the other thing. I think probably the best places to look for dealing with this are um, um, the representational similarity analysis sort of literature where people are trying to compare two neural networks, right? Where you're like not quite trying to compare them, you're trying to compensate for this. So the first RSA methods were really like learning linear projections from one network to the other, just to say how similar are they. But you could instead think of that as a mapping function, right? So you have this mapping function that enables you that you keep up to date somehow to deal with this. On the other hand, I wonder if like my own idea, which I haven't really explored ever, is whether or not we could kind of like operate more in a quantized space where you can think of it like um, um, it's kind of like you have, the output of your system being something like um, 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 it's kind of like what I'll put it like this, right? Like, what if you had a VQ VAE, like a vector quantized VAE, and you can think of that as like, what if you have this in-between network, right? That's kind of like kept frozen that can do this mapping successfully, such that basically it gives you indices and can keep that up to date. But I haven't fully explored that idea. But I just thought maybe if you could have like more of an index-based approach, maybe we could kind of like as a scheme to combat this. But I haven't thought kind of like an idea I've played with in the back of my head maybe a year or two ago, but I haven't attacked it. So, but anyways, it was a good question.
Yeah, the interesting idea. Thank you for sharing.
Thank you. And we have another question from the audience. I can ask. Yes, sure.
Sorry, scientist here. Very inspiring talk. I also am glad you mentioned RSA. I have a question about your thoughts on the continual learning on memorization, more like close to episodic memory, like past relevant feature memorization, not necessarily storage, but more like a past relevant features, and how does that being continuous incrementally deploy in neural task? So just you can just answer in whatever you want. It's a very general question.
Yeah. If you're distinguishing between like an episodic kind of memory,
Yeah,
that
exactly.
think about
So
that
I
as
was
our replay buffer. Incidentally, that's one of the things I feel like we're not even using fully well, right? Like humans can retrieve information from it, kind of like a RAG thing, right? But also we consolidate, right? And continual learning is just treated as this thing for consolidation.
yeah, and also not all the
Um,
information are equally remembered, right? As humans, we sort of
No, 100%, right?
Yeah.
You store what's relevant and probably distill what's relevant versus what's not, right? If it's novel or salient, not redundant, all
Yes.
right? Otherwise,
Yes.
what's the point? Um, um, okay, but your question's actually so it's very close related to the project I currently have Yusuf working on, that student who did the vast majority of the efficient continual learning work I presented. Well, what I've been thinking about is how do we get inductive kind of architectural biases such that we learn a general kind of trunk, you might say, that, for a given input has, basically this trunk has like for each layer, right? Very reusable features, right? But, basically it's extracting reusable features in each layer. So, but then having a separate part of it that's also looking at the same, input to that layer, but determining, hey, which of these do I need to use for this, right? So kind of like conditioned upon the input, which of these general features should I use? Yeah, I'm very interested in that. Like I feel like right now we aren't. No, I will see what happens. So far, he hasn't had any luck, but I really like the idea. It's exactly what I'm thinking about.
Oh, thank you very much. Thank you.
Oh, I guess I can close.
Thank you. So there's no other question. I guess we move to the spotlight presentation. Thank you once again, Chris, for the wonderful presentation.
Well, thank you. My pleasure. Thank you for inviting me.
Okay, so now we have a spotlight paper presentation from full data to few.